Yeah, so one more thing I wanted to highlight for this lab that's kind of important is the convention for the IF bits in your CPSR. So if you look at the ARM 926EJ manual, which is in your VM, when the 2 bits are set, the interrupts are disabled. So if you clear the bits, then the interrupts are enabled. So I also wanted to clarify one more thing. So when I say go in IRQ mode here, on line 35 in your vectors.s, what I'm saying here is to load the mode for the CPSR, because we're actually emulating this in QEMU. So we sort of have to add code to do the mode change manually. And so I could actually give you the 2 pieces of code here. So. Sorry, this wasn't very clear. So. So for go in IRQ mode, I have 2 instructions. One where I mask out the mode bits, essentially, to I clear them to 0. And in the following instruction, I put the actual encoding for the IRQ mode, which is 10010 or hex 12. So if you remember, so the IRQ mode bits is 10010. So all I'm doing here is setting the mode bits in the CPSR register, which has been saved into R0, and setting it to the value in this table. And so you guys tell me what goes here then. So if we want to go back into supervisor mode or emulate going back to supervisor mode, we have to load the mode with the appropriate bits for supervisor, which is actually 10011. So. So sort of what happens here is, since we're emulating this in QEMU, the base address for the vector table isn't actually at 0, because QEMU starts running code at a fixed offset address. And so what ends up happening is the code that's been written here, it actually ends up copying the vector start to vector end. It copies this vector table into the beginning of memory, so at 0. So that's done right here with the branch with link to copy vectors function. And the copy vectors function is actually defined in inter.c. So go here. So copy vectors takes vector start and end, and you see it copies it to destination 0, and then it just starts copying all the entries in the vector table. And all the interrupt handlers are actually defined in this C file. And the one that we're trying to emulate is the IRQ for the serial UART driver. So essentially this lab expects that all the characters that are input from the keyboard are going to be put into UART0DR, which is the data register. And it's actually offset by 0 from this base address. And this was actually provided in the ARM926 manual references. So if you go there, they have a prime cell UART manual, which actually goes through how the UART device works. But suffice it to say, this is an example of the memory mapped I/O that I've been talking about. You can access these hardware peripherals just using memory addresses and just reading it directly from memory. If you notice, there's the volatile keyword being used to define this register. All that means is the memory contents will keep changing, and it's just a warning to the actual OS that's running this to say that that register value can change. And so, and since it is a serial driver and we're emulating it, it has to be defined as volatile. So once you have that data in that register, all you have to do is read it. And so you can, so since we're trying to do something interesting here, we want to see whatever character we input from our keyboard get output after adding 1 to it. So all you do is you take the UART0DR and add 1 and reassign it back to UART-DR, just like Dave said. So. And once that's done, the other part that we had to modify was vectors.s. So this actually defines part of our handler. So this is an example of mixed assembly in C code. You can have some vector interrupt handlers defined in C and some of them defined in the assembly code. You can actually, if you go into enter.c, you can see that some of these variables are defined with the extern keyword. So what that means is these are defined external to the C file. And so if you remember, vector start and end was defined in the assembly file that we had seen. So the way to mix, to reference assembly code in C is you just define it as external. And when the linker comes across these symbols, it links these variables to the one in the assembly object file. So in vectors.s, the solution is actually located in your on the host. Actually, if you go to dot interrupts, actually. So it's located in projects /dot interrupts. So what's happening here is so once we've done our interesting little bit here with the UART driver, we also need to ensure that the reset handler, which is what gets run the first time QEMU boots up, right? If you remember, power on ARM always executes the reset handler, and when you enter a reset, you're put into supervisor mode. So you need to set up the supervisor stack, and this is actually kind of defined in the memory map in your linker script, which is the inter.ld. And it kind of defines where the stack should be put in memory and all those other information. And then it actually makes a call to copy vectors to relocate the vector table in QEMU from wherever it's put in the binary to 0. And once that's done, we actually want to go into IRQ mode and start up our serial driver. So in order to do that, we first have to get the mode from the CPSR and all the contents of the CPSR, put it into R0. We'll treat R0 as our temp variable here. And once we've copied the CPSR, I gave you these 2 lines of code, which essentially sets the mode bits to IRQ mode. And at that point, you're actually emulating switching to IRQ mode, right? Once you've done that, you have to copy the R1, the modified mode bits, back into CPSR. If you remember the convention, so when you use MRS, you provide the register followed by the special register, which is CPSR. So this is saying move to register from special register. And it copies the CPSR into R0. Here, we're writing it back after modifying the IRQ mode bits. And we copy it using move from special register to core register, CPSR followed by R1. So once you're in IRQ mode, you have to set up the IRQ stack. This is sort of done for us because by the hardware, but since we're emulating here, we need to do that. If you remember, the stack pointer is banked in the IRQ mode, so it gets its own special stack space. So all you do is you say, there's already IRQ stack top defined for you in the linker script. So, and then all you have to do is, once you have set up the IRQ mode, you've emulated the switch to the IRQ mode, and you've also switched the stack pointer. Once that's done, then we can enable IRQs. And the way to do that, if you remember, the convention is 0 enables IRQs, 1 disables the IRQs. So you just end up clearing bit 8 or bit 7 if you're using 0-based indexing. And that just translates to 8 here and hex 8. Once that's done, to go back into supervisor mode again, after enabling these IRQs, you do move. If you remember, I copied CPSR into R0, but the modified values I was using R1. So here I just copy it back, move from special register to core register. Actually, it should be move to special register from core register, R0. So it copies the value from R0 back into CPSR. And then it starts executing whatever main code is there. This could be your kernel or whatever. So once you do this, you should be able to actually run it and see the output characters. So this is the kind of work it takes to put an emulator together for bare metal. So we wouldn't have had to do all these things for a actual bare metal hardware, right? It sort of does this for us, but this should give you an idea of how sort of the vector tables work and how the mode changes happen, things like that. So, are there any questions? Oh, so are you looking at the QEMU screen?
Yeah.
Yeah, don't look at the QEMU, look at the host. Okay. So the bare metal actually doesn't have any I/O. So it's actually outputting to the host terminal screen. So if you start typing, you should start seeing output. Sorry if I didn't mention. So first, you run build and start running build. And you have to escape the focus from QEMU, which sort of grabs your focus, hit Alt-Control, go back to the host terminal here. And if you type A, you'll start getting a B out. It's just adding 1. If you type C, you'll get a D out. Yeah, you have to sort of ignore the QEMU screen. So.